Something that you'll find important in this chapter is the difference between geochronology and chronostratigraphy. Geochronology is the study of the time passed since Earth's formation to the present day, and chronostratigraphy is the study of the deposited rocks during each geologic time interval. Each of these has a new vocabulary that we will be discussing in this video. Immediately, the obvious question in the virtual room is, how do geologists and paleontologists estimate the age of rocks or fossils? This practical skill you will practice in your lab section. Geochronology can be defined by two different methods, relative dating and absolute dating. The method of absolute dating wasn't around until the early 20th century with the discovery of radioactivity. Before this, researchers were limited to relative dating, which identifies and sequences geologic events from oldest to the most recent geologic event. Neither of these methods alone can resolve the age of rock layers and the fossils they might contain, but together they have the resulted effect of a surge of understanding in the last 120 years or so. Geochronology provides a numbered timeline on which to place the sequence of events established from evidence in the rock record, studied with chronostratigraphy. The challenges of this pursuit are similar to those of a jigsaw puzzle, except the pieces are scattered across the globe. You might be familiar with the Jurassic period because of the Jurassic Park movies. Oh man, that original movie still really holds up. But it would be not practical to assume that taking this course will make you familiar with the vocabulary of all the other geologic time intervals. Familiarity of this comes from years of practice, using the geologic time scale as a tool. This practical skill will be tested in your lab section. I want you to understand how geologic time is organized, not necessarily memorize the words that are used to describe it. It is not so different from how our time is divided into years, months, and days, except the units of time are eons, eras, periods, and epochs. I will try to summarize the geologic time scale and each of its parts in turn. At the eon level, we have the units Hadean and Archean eons. The first has no rock record, because the world was not fully formed, so it is informally used in the geosciences. The rock record begins with the Archean, and it ends 2,500 million years ago. The next eon, the Proterozoic, takes us right up to the beginnings of life with hard tissue bodies. Think like crab shells and coral reefs and stuff. The overwhelming majority of the fossil record of life is contained in the Phanerozoic Aeon, which is 541 million years to the present day. You may hear paleontologists summarize the time before this simply by using the word Precambrian, so called because the first period of the Phanerozoic Aeon is called the Cambrian period. But let's not get ahead of ourselves, because we skipped the time unit of eras. There are 3 eras within the Phanerozoic Aeon from oldest to the present era. The first, the oldest, is the Paleozoic, and then the Mesozoic, and then the current Cenozoic era. Here are 3 simple ideas about what types of animals each is known for. The Paleozoic era is known for ancient invertebrates, fish, reptiles, and amphibians. The Mesozoic era is known for dinosaurian reptiles, and the Cenozoic is known for the mammals, which are still prevalent today. The smaller time units, periods and epochs, will be explored in your lab section. Here, I am skipping to the difference between these time units and the words used to describe the time rock units. See, the time units are what we've been discussing, but when discussing the representative layers of rock that align with these time units, we introduce space into the study of Earth history. Not every sequence of rock layers represents the entire span of Earth history, and conversely, complete Earth history cannot be recorded and represented by any one sequence of rock layers. When discussing the history of the geologic timescale, the textbook is organized by early research of the rock systems across the globe, from oldest time rock systems to the most recent. This summary of the history of Earth life is discussed in your labs organized by time units, without much regard to the rock units. This section of the textbook is an interesting read, especially as a globe-trotting guide through space and time. But it's more important that we discuss how the absolute ages are calculated for the modern geosciences. For this, we start again with Charles Lyell, who calculated the age of the Cenozoic by comparing fossil changes during the Cenozoic era against the changes that took place just within the Pleistocene epoch. His number was 80 million years for the Cenozoic era, which is only 14 millions more than what modern science tells us. Other attempts to use the thickness of a rock layer and the amount of time to deposit that much sediment to calculate how old the rock layer is. The problem there is that in the modern day, we observe sediment accumulating at rates that sometimes is very high, like during landslides, and sometimes is very low, like the waves crashing on an ocean cliff and creating the sand of the beach. Some early researchers tried to use the amount of saltiness of the oceans, because they assumed that the ocean was pure fresh water when it formed, and that all of the salt came from the streams carving up the mountains and carrying the material to the coastlines into the ocean. Once again, this method didn't work because we observed ocean saltiness change because of physical and chemical interactions. So therefore, the amount of salt in the ocean water does not change consistently through time. It seems like whatever natural event that would eventually work as a clock by which to measure Earth history must also occur at a consistent rate that is unaffected by outside physical and chemical processes. For this, we have to resort to properties of the atoms themselves. So when thinking about this class, I realized that previous videos covered the properties and mechanics of radioactive decay a little bit, which was discovered in 1896 as a means of challenging the idea that the Earth was steadily cooling throughout geologic time. See, radioactivity is a source of new heat that exists in the planet. So if new heat is being generated by radioactivity, then the Earth is not steadily cooling down. Additionally, as the mechanics of radioactivity became better understood, it became the best natural clock around. The subatomic particle ejection from atoms, which is why standing near highly radioactive elements can be dangerous without protection, and it can be sketchy because it's literally tiny particles that can cut through matter by fitting through the space inside of a single atom, of which billions upon billions occupy your body. Okay, let's pause for a second. This is not a particle physics class, so I don't expect you to learn about the details of subatomic particles, but they are a good clock because no matter how hard we try to affect the rate at which these smaller than atom particles are flying out of the center of the atom, we can't make it change. Heat, pressure, chemical, no matter what we do through it all, the radioactivity goes on like nothing is happening. Okay, unpause. So essentially what is happening with radioactivity is the release of subatomic particles until that unstable atom transforms into a new element that no longer releases particles and is stable. So when a radioactive element gets trapped within a crystal structure, that transformation begins. So a researcher can grind up the crystallized rocks and use complex machines to detect the amount of elements that have undergone this transformation. Knowing the rate that this occurs for this specific unstable-stable element relationship allows us to calculate how long the transformation has been going on. This is why igneous rocks are the best rocks for this method, because they formed directly from cooling and crystallization of hot liquid rock and have been relatively unaltered since. The other types of rocks, sedimentary rocks and metamorphic rocks, are formed from the alteration of other rock types that have already formed their crystals. So absolute dating is not possible if the crystals in the rock are originally formed in a different rock, as is the case for sedimentary and metamorphic rocks. Once again, geoscientists must combine this absolute dating method with other techniques that help us determine the age of all rocks, not just igneous rocks. Cue the process of correlating sequences of rock that are separated in space but unified by time. A paleontologist needs rock layers that can be dated absolutely, because if a fossil bed occurs above, below, or in between these layers, then immediately we have relative ages of the fossils enclosed, or bracketed, by a range of years. Additionally, this range can be presumed in another area of space if the same combination of fossil types are found to be present. And you don't even need an igneous rock to be present in that area of space in order to get that date, because the community of fossils enclosed in the sediment layer is the same as those associated with a igneous rock type that has an absolute date calculation. It is important to understand that we cannot predict the exact moments that radioactivity occurs, but when these radioactive events are averaged out over time, we can predict the amount of time for half of the unstable element to decay into its stable element. The process of absolute dating involves the measuring of total amount of sample elements in the rock, the ratio of the unstable and stable elements present, 50-50 for example, and the number of 50% reductions of the unstable element it takes to get to that ratio. That is referred to as a half-life. Now you will get a chance to practice this skill in your lab section. There are several unstable, stable element pairs that are used and discussed in the text, but I want to mention two here, just carbon and fission track dating. Now, essentially, carbon is the most stable when it has 12 protons in its nucleus, or structure in the center of the atom. But the environment is pretty chaotic in the high atmosphere, what with all those cosmic rays from the sun. A lot of carbon atoms, get knocked around and excited from all that energy, and sometimes subatomic particles smack into nitrogen atoms until it forms an unstable form of the carbon atom, with 14 protons instead of 12 in its nucleus. So here's the thing. These unstable carbon atoms get into the bodies of living things the same way stable carbon does. So in the same calculation method as before, we can compare the amount of unstable and stable carbon in recent fossil specimens, no older than 50,000 years or so, to determine how long the animal or plant has stopped taking in fresh unstable carbon. After enough time, all of the unstable carbon will decay, and then the carbon dating method is no longer effective. Finally, I will briefly say that fission track dating is pretty cool, because it is based on counting the cracks in a mineral that represent the physical damage done by the ejected subatomic particles. And that is about all, folks. Geologic time is particularly challenging, so it is appropriate to get it out of the way while we are fresh in this course. And now that we are at the end of the lesson, we can understand how modern science indicates that the age of the Earth is a massive 4.56 billion years. I'm looking forward to answering any questions that you may have regarding this topic and the assignments. So reach out should you have any difficulties applying this information provided in the video. And thanks for watching.